Most people think of air conditioning simply as temperature control. You set a thermostat to 72 degrees, and the system blasts cold air until satisfied. But designing a commercial building's climate system requires mapping out strict thermodynamic boundaries long before a single pipe is routed or duct is sized. To do that accurately, engineers rely on two distinct sets of data. The first is a microscale analysis of human biology. We have to map the exact physiological heat exchange constraints of the human body to define our indoor target. The second is a macroscale analysis of the local climate. We use probabilistic, cumulative frequencies of historical weather patterns to establish the outdoor boundary. By examining both the biological requirements of the occupants and the statistical realities of the local weather, we can deduce the exact physical and statistical conditions that govern the sizing of modern heating and cooling systems. If an engineer fails to accurately calculate the mathematical delta between these two datasets, the resulting system will suffer from chronic inefficiency, and the occupants will never actually feel comfortable. This diagram shows the cylindrical model of the human body's interaction with its environment. The body is not a passive object being acted upon by room air. It is an active metabolic engine that continuously generates and dissipates heat. A typical sedentary adult has a baseline metabolic rate, or MET, that emits approximately 360 BTUs per hour. To prevent hyperthermia, the body relies on three primary avenues of heat dissipation. Energy transfers to the air through convection, to surrounding surfaces through radiation, and moisture leaves the skin through evaporative heat loss. This outward heat transfer is actively modulated by what we wear. Clothing acts as a thermal resistor, measured in Clo units, which dictates how easily metabolic heat can escape the body's surface. Standard engineering calculations assume an insulation volume of 0.5 Clo for typical summer clothing, like a short-sleeved shirt and light slacks. For winter, that value increases to 0.9 Clo to account for heavier fabrics and layers. Achieving thermal comfort requires balancing a dynamic, continuously regulating heat flux equation, rather than simply satisfying a static room temperature preference. Imagine sitting by a large single-pane window on a freezing day. The thermostat reads a perfect 72 degrees, yet you find yourself shivering. That physical response occurs because the cold glass acts as a massive radiant heat sink. It continuously pulls thermal energy directly away from your body, bypassing the warm air entirely. To account for this, engineers calculate the mean radiant temperature, or MRT. This is the weighted average temperature of all the surrounding surfaces in a room: the walls, the floor, the ceiling, and the windows. Combining these variables gives us the true metric for human comfort: operative temperature. By averaging a 72-degree air temperature with a 50-degree mean radiant temperature near that cold window, the calculation yields an operative temperature of just 61 degrees. This chart from ASHRAE Standard 55 maps those operative temperatures against humidity to define the acceptable environmental conditions for human occupancy. Notice the two distinct polygons on the graph. The required operative temperature range shifts noticeably depending on whether occupants are wearing 1.0 Clo winter clothing or 0.5 Clo summer clothing. These zones are further constrained by absolute humidity. The upper limit is capped at a humidity ratio of 0.012 to manage perspiration, while the lower limit is dictated by a minimum dew point temperature to prevent the drying of skin and mucous membranes. This mathematically bounded psychrometric polygon forms the precise, non-negotiable physiological target for the indoor environment. Once the internal target is set, engineers must look outside the building. Calculating thermal loads requires highly specific local climatic data. You might assume that a building's equipment is sized to handle the absolute hottest or coldest day in a city's recorded history. It is not. Sizing a system for a historical maximum guarantees chronic equipment oversizing. The system would spend almost its entire life operating at partial load, resulting in reduced mechanical efficiency and an inability to run long enough to properly dehumidify the air. To solve this, the industry relies on cumulative frequency percentiles to establish realistic statistical ceilings. Looking at the data for Boise, Idaho, we use the 0.4. A peak dry bulb temperature of 98.7 degrees represents a threshold that will only be exceeded for about 35 hours in a typical year. Directly adjacent to that value is the mean coincident wet bulb temperature, in this case 63.7 degrees. This coincident metric is vital because absolute peak dry bulb temperatures rarely occur at the exact same moment as absolute peak humidity. By pairing the peak dry bulb temperature with its concurrent average wet bulb temperature, engineers calculate a realistic, simultaneous, sensible, and latent load. They avoid compounding worst-case variables that simply do not exist together in the real world. The entire purpose of a building load calculation is to precisely quantify the gap between these two datasets. On one side, the biological floor, a 75-degree operative target. On the other side, the outdoor statistical ceiling, firmly capped by historical climatic percentiles. The size, capacity, and distribution of every single piece of heating and cooling equipment in a commercial building is strictly governed by this calculated differential. Mastering that specific delta is exactly what separates brute force temperature control from true engineering of the built environment. By accurately mapping the biological limitations of the human body against the statistical realities of the local climate, we ensure that our architecture remains both highly efficient and deeply comfortable.